We talked about in the last video how metals aren't covalently or ionically bonded. They're bonded metallically, which means that any specific given electron is not stuck to a nucleus, but rather is allowed to flow freely throughout the structure. It explains why glass, rubber, and wood aren't very good electrical conductors, but metals are. And that's because of this sea of electron effect. The second effect is the energy bands effect, because rather than discrete energy levels, like in a single atom, multiple metallic nuclei will actually cause for there to be a full band of energies that the electrons can exist at, and this will allow for different continuous states of energies for the electrons. So now we can consider some ideas about how electrons will flow through a structure. And the first is the current of the electrons. If I put 3 electrons on the left side of this wire and somehow I push them over to the right side, because these electrons aren't stuck to any specific nucleus inside of the wire, they'll be able to flow freely from the left to the right side. The amount of electrons that flow through and how quickly they flow is equivalent to the amount of current through the wire. You can have a lot of electrons flow very slowly through the wire, or you can have a few electrons flow very quickly through the wire, but this is both equivalent to the same amount of current. And it's similar to water flowing through a pipe, which is why the water analogy is used sometimes. But anyways, reiterating, current is how many electrons are flowing through that copper wire per second. But next, consider the fact that there's a bunch of nuclei inside of this wire. So the electrons aren't going to take a perfectly straight path. What's going to happen is that these electrons, as they flow through, they're going to get deflected and bounce off of these different nuclei and take a very curved and uneven path through the structure. What this ends up happening is now the electrons won't flow as quickly through, so that means your current will go down. Now, different structures will actually be different in that of how bumpy they are. The bumpiness of the electron path is what we kind of refer to as resistivity. Now, different materials have different amounts of resistivity. For example, it's pretty evident that metals will have a very low amount of resistivity, while structures like rubber, glass, air that don't conduct electricity have a lot more resistivity. So, kind of going back to it, current is the flow of electrons, and resistivity is how much the electrons are slowed down because of this curved path they have to take. A couple more things that we sometimes think about, though, is the opening of the wire, how large this area is, because obviously the larger this is, the more electrons can pass through. We think about the length of this, because if the electrons have to flow through a longer length, that means that they'll have to pass through more and more nuclei, which means more opportunities for it to slow down. So typically this is written as the overall resistance. How much are electrons resisted from going through is equal to this resistivity, which is written as rho, times the length of the wire, because a longer length means more resistance, and then divided by the area, because more area means that now more electrons can pass through, so it's not as resistant. And so these are two very fundamental ideas, and I hope it kind of makes some intuitive sense because all that's happening is these electrons are just wanting to flow through, but as they flow through, they're bounced around by these different metal nuclei. But let's think about the energy of the electrons as they flow through the structure. Because if you think about it, if they get bounced around, well, they're also going to lose a lot of energy. So if I put a bunch of nuclei across the bottom here, and I think about electrons moving from the left to the right of the structure, well, they're not going to move perfectly across. They're going to exist inside of their energy band, and as they move across, certain nuclei will attract and deflect the electron. So it's going to come across this path and then interact with this nucleus. What's going to happen is this nucleus is going to deflect the electron, and then both the electron and the nucleus will actually start vibrating. And this is given off as heat. So the electron is attracted to the nucleus is attracted to the electron, and it's going to start vibrating the two. So the whole structure begins to heat up, and that energy from the heat is lost from the electron. As this electron flows through, it's going to lose some more energy in a heat exchange with this other nucleus as it gets deflected. And so as an electron flows through a wire, it slowly loses the amount of energy that it has. We call this loss in energy the voltage drop of the electron, or just an energy loss in the heat exchange. It explains why your phone heats up over time and why different electrical components heat up, because energy is being lost as it flows through structures and wires. Now, I talk about voltage because what voltage is it's just energy divided by the charge of the electron, which is normally written as Q. So all that means is voltage is just the same as energy, just we're forgetting about the fact that it's electrons and just dividing that value away. So it's actually not too difficult of an idea. There's current of electrons flowing through, which are resisted because of the structure of the atoms inside of the copper wire. And as the electrons flow through, they interact with the nuclei and slowly lose energy over time.